Hello and welcome to this video. Today we will go over another problem from leetcode. It's called count stepping numbers in range. As we can see, it's classified as a hard problem, so let's just go over the requirements. We are given a range of low and high that are represented by low and high numbers, which are strings actually. So they don't have a integer representation, but they are strings. And we need to count all the stepping numbers that are between this range. And the stepping number is classified as number which digits are the digit differs with the digit before it with only one number. So for example, if we go here and try to come up with some number that's stepping, let's say first digit is, yeah, so let's say the first digit is 2. Let's make it, it's okay. So yeah, so the first digit is 2. The next digit should be different from 2. Should be different with from 2 by 1. So it's gonna be either 3 or it can be 1, right? So the next one that comes after 3 can be 4 or can be 2. The one comes after 1 can be 2, can be 0. The one comes after 0 can only be 1 because 0, there's nothing that's less than a 0 by 1. The one that comes after 2 can be 1, 3, and so on. So this is like one example. So for example, one number would be 2, 3, 2, 1. So we have all the numbers differ from each other by 1. They are either less than the previous one or bigger than the previous one, but the difference is 1. So this is the requirement. As we can see, it's a hard problem, so let's try to solve this with several steps. And don't let's not forget to consider what constraints we have. So as we can see, the numbers can be up to can have up to 100 digits. So that's gonna direct us when we try to optimize the solution to see if we can find a solution that doesn't get time out exception. Yeah, so we have the example, and one thing to that comes to mind is that we can always generate all of the possible numbers and always count them. So for example, if we start generating with having a first number being 1, we know that the next number is going to be either 2 or is going to be 0. If the first number is 2, the next one is going to be either 3 or 1. If it's 3, the next one is 4, 2, and so on. And so if it's 9, then the next number can only be 8. So this is one possibility. So we have like, so for the first number we have this many possible, this many possible solutions. For the second number we have this many, and so on. So we can always generate all of the numbers that we want and just count them. So let's just do this. I've already done some solutions, so let's just look at what I've come up with. This is the first solution. It's just supposed to count all the uh, numbers, all the stepping numbers that are of a specified length. So for example, in this case, I'm taking the length of the lower bound and just counting all the numbers that are of that length. We can run this in the leetcode to see how it behaves. But first, let's just analyze the code, or we can analyze it. Yeah, let's run it and we can analyze it later. So yeah, it's obviously not gonna pass the test cases they have. So but we can come up with our own test case. Let's say we want to count all the numbers from 1000 until 9999. Okay, so the third case succeeded because it counts all the numbers basically that have length 4, and these are all the numbers that fall into our range. That's why this test case succeeded. So let's note how it is generating the numbers. So it has a two-dimensional array, and for each number, for each index in this array, the corresponding one-dimensional array contains all the numbers that can be the next one. So for example, for the index 0, the only number that can be the next one is 1. For the index 1, the two numbers are 2 or 0. This is what we have shown here, right? So for the 1, it's 2 or 0. For the index 2, it's 3 or 1. That's we've shown here. We also we also have we are using recursion because we see the constraint says that the longest number can be is like 100 digits, which is gonna mean like we will have 100 calls, and this is not gonna overwhelm our stack, and we will not get a stack overflow exception. So we can just use recursion here. So after we decide which length we want to count numbers for, we have a current path. This is basically the current generated string that we have. So if let's assume the length that we have is 4 in our example. So if the length is 4, and we want to count, yeah, if the length is 4 and we want to count the numbers that have the length 4. Let's say in the path that in the current path we will, for example, have 1, and on the next recursive call we will add 2, and we will keep adding this, and this is just will keep the record for the current number that's generated. But this is not Uh, this is just for keeping the because we are later going to use this number to get the so we are using this number from the path to get the next numbers that we are going to add to the array to our stepping number. That's why we store those. Uh, yeah, so we can see it's generating all the numbers in the that have the specified length by going over all the next integers that we have here. You can you can look up the solution. I will link it in the description. The next we know that we have multiple ranges, right? We don't just have one a multiple length. We don't just have one length. So for this uh, we need to consider all the lengths that are between the lower bound and upper bound lengths. Uh, in this example, this is the second file. So here we can see, just copy this one as well. Okay, so let's add another test case. So this test case will have mm, lower and higher numbers will have different lengths. So instead of 9,000, we will choose 9 and 99,000. Okay, so the upper bound has length 5, lower bound has length 4. So we have to count all the stepping numbers between these. Yeah, it succeeded, and this code only adds this for loop, which is just going over all of the possible lengths from lower to higher bound lengths, just calling the same get count function. This is all that the solution is. Okay, so both of these solutions count all the numbers that have the specified length, but they don't consider the lower and upper bounds. As the problem says, we should consider all the numbers that are between the lower and higher bounds. In this case, we don't. So let's add that part. Okay. So in order to uh, easily compare the numbers from lower and higher bounds, we are converting them into list of integers that we can easily we can later compare these integers with the integers we are generating and see if they are uh, higher or lower than what we are looking for. One thing to note is that uh, when generating numbers, we only need to consider, uh, we can consider the full number, of course, like after we finish generating it, let's say we have our range is, so that's our lower bound is, let's first clear all of this. Yeah, let's say the lower bound is 1310 and upper bound is 9800. So for example, when we start generating, first we will generate 1, then we will see, oh, the next number can be 2, then the next number can be 3, then the next 4. So this is a value, this is a stepping uh, number, but it is outside of these bounds because it's less than lower bound. And we can detect this while we are generating it. So how we do this? So first we get first one, right? We see that uh, it matches with the first number in our lower bound. So we know that whatever comes next, we should check if the if this number is below the corresponding number in the lower bound. We will know that anything that is generated afterwards will also be lower than the lower bound. So for example, if the next number is 2, we know that anything we get here, any number, like even the biggest possible one is 99, we will always be lower than this our lower bound. So we don't have to consider generate any number that after we find out that this 2 is less than the 3. So that's what is displayed here. Like we okay, so that's what is done here. First, as I said, we generate the list of integers for our convenience that we're going to use later. And as I said, whenever the length is the same length as the lower bound, that's our case, right? The length is 4, the lower bound is 4, lower bound length is 4. We see if the first number we generate is less than the first number of the lower bound, and in this case we just skip this. In case of the higher bound, the same. If we see the first number we generate is bigger than the higher bound, we also skip this. So in case of a lower, let's say the higher bound is not 9, but it is 8. 8, right? So whenever we are generating and we have, for example, reached the number 9, we have our upper bound. We know, so the first number is 9. We see it's bigger than the 8. So we know that anything we generate is going to be out of the bounds. So that's why we are ruling out this by just calling continue. And we decide to check if we are lower than if we are outside of the bounds based on this condition. So if the number we are generating has the same length of lower bound, and the number that and the first integer that we are generating is actually this one should be equal to the first integer of the lower bound. We know that we should keep checking, as in this example, like we know the first one was equal, so we checked the next one. So that's the same logic here. Like if the first one is equal, we will keep checking this in the next calls to the function, which we do here. So this is what we receive, and if we have true, we always check if we are less than the lower bound, we skip this. If we are equal to the lower bound, we know that the next function that we are going to call should also check. So for example, in this case, the one, if the number generated is 1 and 3, we know the next function we call should keep checking, because what if this one, I guess this one cannot be lower than, uh, but what if it was like, what if this one was not 1 but was 6? In this case, if we had 3, 2, oh, this one would be again smaller than the bound, and we would need to skip everything generated after it. So that's the next equals lower bound. That says, should we keep checking or should we not? And the same one goes with the upper bound. So if we have, if the function calling us tells us to check the upper bound, we check the current generated digit with the uh, corresponding digit in the upper bound. If we are over it, we skip it. If we are equal, we keep checking. If we are less than the upper bound, we can stop checking because we are definitely not going to cross the bounds. And this code is the same as before, just adding this newly generated booleans to the code. So this one should consider the ranges. So instead of having, you can add another test case. So instead of having 1000 we can have 1200, for example, and the lower range can be upper range can be 8000. So this should work because we already oh, okay, so this already is succeeding and all of the test cases are succeeding because they are small numbers. And most importantly, our test case succeeded, which means we are considering and we are ruling out the numbers that are outside of the bounds. But this case is gonna still fail because the we are not, so the total number of all the possible solutions can be very high when the high and when the upper bound is too big. So for example, we can have as much as 100 digits as the problem says, but let's say we have not 100 but a lot more than a few digits. And we can see that this is gonna time out because uh, because we generate just too many possible solutions. So we should consider how to optimize this. Let's draw a, let's first remove everything. And let's draw something that's gonna help us figure out. So we said, for example, we are starting from number 1. Next one can be either 2 or 0. This one can be either 3 or 1, either 1. Oh, it cannot be anything else. So here we can see that, so this one can be 2 or 0, this one also 2 or 0. So we can see that this subtree and this subtree, this sub solution, as we call it, is gonna be the same as this one because we are uh, starting from the same number 1. The length is the same, so we have considered 1, 2. This is the third digit, so the length is the same. the starting point is the same. The only thing that is different is this 0 and 2, which doesn't affect this part at all. So everything here that we generate, every number is going to be the same as here. They are exactly the same. So this tells us that we are doing a duplicate work. But we don't have to. We can remember once we generate numbers for this one, once we count everything here, we can just remember it, and whenever we are back here, we get this. We get we know that we are on the digit 1, and we know the length is 3. So we know that everything we generate is going to be the same as here. We can just get this number and add it to our account. This is what is done in this full solution. You just copy it here. Yeah, so the only thing we added here is going to be this cache for memorizing the solutions that we already computed. I'm initializing the cache values with -1, so whenever we see a -1, we know that this is not yet initialized and we have to count. The only thing here is added is that we are checking if we already have this number. If it's bigger than 0, that means we have already computed something and we return it. And please note that we are only considering this cache if we don't have a problem with checking the bounds. Because if we are checking the bounds, that means we are not considering all of the numbers in this in the generated graph. So if for example it comes up that the bound doesn't allow us to go over, let's say 1 2 1 2 1 2. Okay, so let's say that bound says it should be less than 1 2 1. All right. So this is, for example, our bound. First 4 digits of our bound, lower bound. Or no, upper bound, sorry. So this is the first 4 digits of our upper bound. This means that we cannot consider all of the solutions in here because this one is going to be 1 2, right? 1 and 2. So 1 2 1 2 is bigger than our upper bound. So we are not, so for this one, we are not going to count all of the solutions in this subtree. But for this one, we are going to count all of the solutions. Actually, no. We still are not going to count all of the solutions. We are going to count all of the solutions because the second number is already less than 2. And whatever we generate here is going to be less than our higher bound. So we are going to consider all of the numbers here, and we are not going to consider all of the numbers here. That's why in this case we cannot rely on the cache. So whenever we have to count consider the bounds, we just don't look at the cache and we go and count all the numbers in this case. And same here, like if we have considered the cache, if we were told to consider the cache, we are just assuming that we might have removed some possible solutions. So we are not saving it. So we are saving only when we have not considered the cache and we know that we counted all of the is all of the numbers in this range. If we have skipped some, may have skipped some of them, we don't count them. So this is the final solution. Let's run it. And it's accepted. Let's, the last one also accepted, and yeah, that solution is accepted by the leetcode, and it passed all of the tests. I will link the code in the description so you can go over it. Yeah, this was another solution based on the dynamic programming, and we saw that if we approach a solution from trying to go from simple case to the harder case, we come up with a solution that's easy to understand, easier to implement than if we were going from if we were trying to solve the whole solution from the beginning. That's it. Thank you. Thank you for watching, and wait for my next videos. Bye.